So in this video, we're going to start Unit 4, Two-Dimensional Kinematics. Specifically, we're going to call this horizontal projectile motion. So first, what is a projectile? A projectile is any object that's launched into the air without its own power. That is what we call a projectile. So for example, if we take a tennis ball and throw it up into the air, that is a projectile. If you throw a football, as soon as it leaves your hand, it's a projectile. Anything that is launched without its own power, once it has stopped being, for example, pushed by your hand, it is going to be a projectile. When we analyze the motion of projectiles, we have to treat them a little bit differently than we're used to. We have to separate it into its horizontal and vertical motion. So for example, if you see the picture, we're going to look at how it's moving horizontally different than how it's moving vertically. We're going to be separating it into vertical and horizontal motion. Now, when we look at horizontal motion, the velocity of our object is going to be constant. The horizontal motion is always going to stay the same. It's never going to speed up. It's never going to slow down. It's going to be constant. But for vertical velocity, that's the falling part, your object is going to be in free fall. It is going to increase its velocity because of the acceleration due to gravity. So just like free fall, it's going to start out at rest, and then its velocity is going to get bigger and bigger as it falls, as acceleration causes it to increase. So if we look at what it looks like with a projectile, if we take pictures of it at specific points in time, so every 0.1 second or so, then we would see that that projectile, if we look at it on the horizontal, the distance between all our pictures is going to stay the same. When it falls, however, if we look at it vertically, it's going to be very close to the same vertical distance at first, but that distance between our successive pictures is going to get bigger and bigger as the speed gets larger and larger and covers larger distances. Now, this is an illustration, but if we do exactly this for real objects, if we take pictures at specific times, you can see it when they get layered on top of each other. So if we look at the vertical or the horizontal distance between these distances are about the same because the horizontal velocity is constant. But if I look at the vertical distances, these are very close together, but then they're starting to get bigger and bigger as the object gets closer to the top. So we can see the same thing with, for example, this motorcycle. If this is our top right here, so this part would be when it's falling. So here, vertically, there isn't a lot of different distance between them. It's starting to fall. But if we look vertically, the distance between them is getting bigger and bigger. But horizontally, these distances are going to be about the same. The horizontal velocity is constant. The vertical velocity is free fall. Now, when we look at the part going up and the part going down, those are going to be mirror images. So this one was going up, but if we go backward, it's going to show us exactly the same thing for if we'd had the pictures going the rest of the other direction. So here's a third picture. This is a stunt, but the same thing is happening. You can see this parabolic motion, and here's the top. If we look at center of mass, if I look at the successive pictures, here, here, here. If I look at these distances between them, if I'd drawn this in the correct location the first time, those distances are going to be the same, constant velocity. But these are very close to the same height. This one's fallen a lot more, fallen even more. So our distances this way are going to be getting bigger and bigger. That is how we look at projectile motion. We have to separate our two motions. So a couple of other things you need to know about this. At the top of a projectile's path, so right here, the vertical velocity is going to be 0. So this is just like when we throw the tennis ball straight up into the air. At the very top, it instantaneously comes to rest before it starts falling back downward. So vertically, the velocity is 0, but horizontally, the velocity is the same. Every single one of these basketballs has the exact same horizontal velocity. The horizontal velocity will not change. At every single point, the acceleration is 9.8 meters per second squared, and it's always pointed down. If instead of looking at the top, if we look at the bottom of a projectile's path, down here, the vertical velocity is no longer 0. It's going to be some bigger number. It's going to start at 0, and it's going to get bigger. The velocity is going to increase as it falls. But the acceleration is always going to be the same, 9.8, doesn't matter where it is, every one of these. And the horizontal velocity is still going to be constant at every single location. So, some important facts. Projectile motion problems are solved treating horizontal and vertical motion separately. You need to know gravity only affects the vertical motion. In vertical motion, we are in free fall. The horizontal velocity does not change. It remains constant. Time in the air is directly related to the release height. If objects are released from the same height, they will hit the ground at the same time. Mass does not affect a projectile, period. So let's go ahead and identify some variables. So we're going to change a little bit how we identify our variables because we are going to be dealing with both horizontal and vertical motion. So when we look at our vertical velocity, instead of calling it initial velocity or average velocity, we're going to call it the horizontal velocity. Hold on, sorry. My pen decided to do weird things. So we're going to call it V sub h for horizontal velocity. And remember, whatever it is, it's going to be constant. When we talk about vertical, we're going to go ahead and use our initial velocity because we are going to have changes. We are still going to have our initial velocity, and for you that's going to be an I, and it's going to start out as 0. As the ball falls, the velocity vertically is going to get bigger until we get our final vertical velocity. When we look at the height that it's falling, instead of using delta D, we're going to go ahead and use h. So this is going to be the height, how far it falls. When we look at acceleration, acceleration is still going to be a, and it is still going to be 9.8 meters per second squared. And then when we look at how far away from the base of the building our ball lands, we're going to go ahead and keep that our delta D. That's our how far. So this is just a couple of the variables we're going to change a little bit. And now let's look at some facts about them, some things you need to know. So when we solve horizontal projectile motion problems, remember, we look on the horizontal axis. There is no horizontal acceleration. The horizontal velocity is constant. And that means that we are always going to use the constant velocity equation. But instead of V average, we're going to use VH just to keep them separate. So this is the equation that we will always use for horizontal information. Now for vertical, remember the initial vertical velocity is 0. Gravity only affects the vertical motion. That means the object is in free fall. It is accelerating. And we will always use the same equation. So of those kinematics equations, this is the one we're always going to use. But we've replaced our, instead of delta D, we're going to call it the height. And instead of A, we're just going to go ahead and put in G. Now, one of the things you might be Well, one of the things you need to know is that time is the same for both vertical and horizontal motion. Time is what connects the two of them. So this is how we set up our equations. So instead of just having, like we did before with free fall, instead of just having our 5 variables, we are going to know that our initial velocity is 0. We are going to know that we are not going to get information about our final velocity. Our acceleration is always going to be 9.8, and so we are either going to be looking for the height or we're going to be looking for the time. So using this information, we are going to know that. If we need to find time, this is the equation we will use. All we did is we took this equation here and rearranged it to get this equation. So make sure that you have this written down. If we are looking for information over here, then again, we will always use our constant velocity equation. So it depends on what information we're given as to what equation we're going to use. We're just going to be looking a little differently to find this. So let's go ahead and do 2 examples. So here we have a student kicks a ball off the roof of a 30-meter high building with a horizontal speed of 5 meters per second. How long will it take for the ball to hit the ground? So we know that the building is 30 meters high. That's going to be our height, 30 meters, with a horizontal speed of 5 meters per second. So that is our horizontal constant velocity. We want to know how long will the ball take to hit the ground. So time is what we're looking for. So looking at both sides of this, do we have enough information to solve the problem using our constant velocity information? No, we don't, because we don't have any information about the distance. So we can't use our equation on this side to solve the problem. So now let's look at the other side. Well, we have 3 pieces of information. We are looking for our 4th. This is our no info. So this is where we are going to look to solve the problem. And since we're looking for time, this is the equation we're going to use. So time is equal to the square root of 2 times our height of 30 meters divided by our acceleration due to gravity of 9.8. And if I do that calculation, I'm going to get 2.47 seconds. So the ball is going to fall in 2.47 seconds. That's how long it's going to take to hit the ground. Now, using this information, now that I know that this is 2.47 seconds, I could take this and find out how far from the base of the building it's going to fall. So by rearranging this equation a little bit, my distance is going to equal, multiply both sides times t, my horizontal velocity times time. So that would be 5 meters per second times my time of 2.47 seconds. And the distance would be 12.35 meters. The next example, a student kicks a ball off the roof of a 10-meter high building, so that's going to be our height, with a horizontal speed of 5 meters per second, hasn't changed. If the ball took 1.4 seconds to hit the ground, how far from the base of the building does it land? Well, how far from the base of the building is our delta D? So this time we are going to be using this equation. And to rearrange it to solve for delta D, I have to move the t from this side to the other. So I'm going to multiply both sides by t. These t's cancel, and the distance is going to equal our horizontal velocity times time. So that's going to be our 5 meters per second times our 1.4 seconds, and the distance is going to be exactly 7 meters. Now the next one's a multiple choice question. So if a ball rolls off a table with different speeds and follows the trajectory shown below, the time between leaving the table and hitting the floor will be greatest for which of these balls? Is it going to be trajectory A, B, C, either A, B, or C depending on the mass of the ball, or is it going to be E? The time will be the same for all 3 paths of the ball. Think about it and answer the question. The answer is going to be E. Remember, if all of the balls fall the same height, they will hit the ground at the same time. The horizontal distance of the horizontal velocity does not matter, does not affect the time to hit the ground. The horizontal velocity is only going to affect how far it gets from the base of the table.